my name is Amy Throckmorton. I'm an associate professor of biomedical engineering here at Drexel University, and it's really a pleasure to have the opportunity to speak with you about my research program and a little bit about Drexel Biomedical Engineering, the innovators, makers, and game changers, that are really changing the world by developing life-saving solutions for all of us. And really the motivation behind my research, stems from heart failure. There are 23 million patients with congestive heart failure worldwide. Over 125,000 of these patients could benefit from a donor organ that was readily available to be surgically implanted. Unfortunately, only 3,600 donor hearts are available each year, and drugs are fantastic. They slow the progression of the disease, but it's definitely not a silver bullet. It's not going to, completely reverse the disease itself. It's merely going to slow the progression of it. And as a result, lots of different devices have been developed, including mechanical or circulatory assist devices. And these particular pumps are used as a bridge to recovery, bridge to transplantation, or even long-term destination therapy, since there are patients who simply don't qualify for a heart transplant. And what I'd like to do is draw your attention over here. This is a typical schematic of an implant of a ventricular assist device or a blood pump that will help to impart energy to the blood and thereby helping to circulate and restore the cardiovascular system to normal hemodynamic levels. And this particular pump, the device, it's a centrifugal pump like a hockey puck, or you think of a housing around a boat propeller. And this device works in parallel with a native heart. Most of these parts are fully implantable. You can see the power cord coming out through the abdominal wall right there in the stomach, a controller, a battery pack holster to be able to provide the power for this particular device. So very much a conventional heart pump that's being used to support patients. Now the work in my research program is also very similar to other faculty here at Drexel. It really lies at the intersection of engineering, business, and medicine. Engineering, the pump design, the materials, manufacturing aspects, certainly the experimental testing, the business aspects, targeting an unmet need, the regulatory process, how to get this device from the bench to the bedside to really be able to save lives and help patients. So the commercialization aspects. And of course, medicine. We have to have that clinical perspective, understanding the cardiology, the cardiovascular system, and the surgical aspects for implanting the device. And also understanding whether or not we have a situation of having an acquired or congenital heart disease in addition to congestive heart failure. So we're talking about, for instance, pediatric patients as well as adult patients who could potentially have heart failure. And for my research program, the BioCirc Lab, our overarching goal is to improve the treatment strategies and therapeutic options for patients with heart failure. And we're going to do this in three different ways. The first way is to integrate innovative design features. So we're going to advance the state-of-the-art by integrating new, smaller design features to make the devices more compact and to make them more efficient. We're going to design entirely new product lines, and we've already done that in my research program for heart failure patients. And we're also going to look at new methods, perhaps software, that can help to support product development and making these devices safer for the patients and more effective for clinical treatment. And students here at Drexel have the opportunity to participate in all of these different objectives and to assist with all of these projects. And I'm only one research program, and there are dozens all over campus that have similar objectives. So the devices that are under development, and I'm just going to share two that we're working on primarily. One is an intravascular cable pulmonary assist device. And this type of device is inserted into the leg, kind of similar to a cardiovascular stent. It's deployed in the leg and then advanced closer to the heart, and then everything unfolds and it's able to rotate and impart energy to the blood. Really, it's a booster pump. The other device I'm working on is a continuous flow total artificial heart. We're calling this the Drexel Dragon Heart, and it's really meant for smaller people. So this could potentially be pediatric patients as well as women, and really patients all over the world who are just smaller than Americans are. And the broader impact of this is really to address complex and unresolved hurdles in the field of heart failure and mechanical circulatory support, advancing the state of the art, creating devices that will bridge the bench to the bedside, and developing translational solutions and new life-saving solutions for patients all over the world. Now, this is a concept where we're developing a pediatric ventricular assist device. And you can see here that we're making use of magnets that are strategically placed in the housing of the pump and within the rotating impeller part that really imparts energy to the blood. And we're going to levitate that impeller within the pump housing and then use bearings, permanent magnets, to really be able to induce rotation using a standard motor. And this has worked very well. It's third generation technology in my field. In addition to this, I mentioned the Cable Pulmonary Assist device, and this is an example of one of those designs. We have several. You can see how the complexity of it, everything in the gray color, that will be the protective cage, and that really expands out into the vessel, and those surfaces remain stationary. And everything that you see in blue would be the impeller and the impeller blades. And if you think of a boat propeller, thrusting the water forward, displacing the water volume so that the boat will move, that's what an impeller will ultimately do as well. Really thrusting, adding that energy to the blood to be able to push it forward and act as a booster pump. This can help lots of patients, in particular those who have right-sided heart failure. In addition, this is the Dragon Heart, and we are making use of space within a centrifugal pump. And right in the middle, there's a spindle region where I've dropped an axial flow blood pump. And so we have two pumps in one, and it really has the ability to almost be a one-stop shop in the sense that it can provide right ventricular assist, left ventricular assist, and perhaps both at the same time. And it's a really compact device, smaller than any device, any total artificial heart that's out there, and definitely comparable in size to any other LVAD or ventricular assist device that's being developed. And we're hoping to continue to make it smaller so that it will fit into a wider range of patients. And this is what we're doing at Drexel. We're doing this in my lab in the BioCirc, and I have lots of students who are helping me to achieve these objectives. The development approach involves a parallel effort where we have computational studies and experimental studies. And certainly I can design anything I need to using the computer, but we need to validate that design. So we build prototypes, we test, we optimize, and we continue through that cycle prior to, of course, testing the device in an animal. And this is just to show you, this is an axial flow blood pump where it's more of a tubular configuration. You can see the inlet and the outlet are along the same axis. And the inlet, of course, will be located right over here, right in this region. And I'm just going to show you, it's a quick simulation where you have the blade, the impeller blades are spinning. And you can see at the inlet, we have blue color, lighter blue, that's low energy. And up at the outlet of the pump, you can see pink and red colors indicating a really high energy flow. And that's what a pump should do. It should impart energy and generate a much higher pressure at the outlet of the device. I mean, that's ultimately what our native heart does as well. And this is just showing you a centrifugal blood pump. It's a pediatric artificial heart. And again, that hockey puck configuration looks a little bit like a boat propeller in a way. But looking at regions where we have forces that could damage the red blood cells or activate platelets. So we have to be very aware of the different fluid dynamic conditions within the pump. And another approach that we use is really interfacing the device design with the physiology. And we take MRI data sets of patients, we stack them, we generate a point cloud that gives us a surface configuration of the vessels, and then from there we can generate a 3D model. And that's what you're seeing here. We use a software called Mimics to do this. And this is a pretty exciting software package that can be used pretty easily to develop these types of evaluation. And this right here is just showing you imported MRI pictures, and you can see the heart in the middle, different vessels, and a lot of artifact. And we will sit with radiologists and just chip away at all of the artifacts so that we can hone in on the vessels that we're interested in. And those vessels can be used, we can insert a device into the space. We can look at what might happen downstream from a pump. There are lots of different ways to be able to incorporate this and look at the effectiveness of our pump technology. And it's exciting to be able to look at fit and other aspects as well with this type of approach. This is just showing you another view of using mimics and being able to really extend out into those vessels when we're putting a pump into one of the major blood vessels, such as the inferior vena cava. I mentioned testing prototypes. We have a modular test loop. It looks a little bit like this, where we can test any prototype that we're interested in and be able to reconfigure it and continue to evaluate pumps. You're looking at the pressure, the flow rate, and of course the rotational speed of those devices. So hemolysis is very important. We don't want to damage those red blood cells. And so we can actually perform these types of studies as well in my research program. It's very important to know how gentle the pump is and to have a better understanding of those fluid forces. We all love to play with lasers, and so one technique that's used is what is called particle image velocimetry, and we can inject buoyant seated particles within the flow, within perhaps a water-glycerin mixture, and then we can use a laser to illuminate a 2D plane within the flow domain, and then we can actually track those buoyant seated particles. And that's what you see here on the upper right. You can see a stacked image set of really tracking, and it gives you a 3D perspective of what's happening in the flow in the pump. And this is showing that not only can we look at specific regions of the pump, but we can also build a prototype of the physiology. We can look at the vessel structure, and we can clearly analyze the fluid dynamics within that geometry. And that's what we've seen here, using programming to be able to reconfigure and stack those images to generate a nice 3D profile of the flow domain. Prototyping is definitely a critically important aspect of developing these devices and making sure that they can support life and that they're safe. And this is showing you one of an earlier prototype that we had developed and that it was used in a sheep study. So 2,000 to 3,000 children are born each year with significant malformations of their heart chambers, and there are very few, if any, therapeutic options available for them except a heart transplant. Well, to address this unmet need, we are developing a blood pump, a percutaneously deployed blood pump. If you think of a boat propeller, for example, it spins, it rotates, and you have that forward thrust, pushes the boat, displaces the water, everything moves. Well, that's basically what a pump will do. So this is one of our Fontan blood pump designs, and you can see it's about 14 millimeters in diameter. And once we start to spin the pump, we're going to be imparting energy to the fluid and pushing blood up through the cardiovascular system. And really what we're trying to achieve with this shape is to adjust the pressure in the circulatory system. So it is because of Drexel University that my US-based research team now has this international partnership with Hebrew University and the Hadassah Medical Center. And bringing with that comes research experience, new resources, and it's a win-win because we're all in this together, we're all developing these devices that will help to save lives, not only in the US, but worldwide. Well, thank you so much for the opportunity to share with you just a little bit about my research program here at Drexel University. To give you a snapshot into the research program of just one faculty member when there are more than 40 of us in biomedical engineering here at Drexel. The opportunities for students are tremendous. Feel free to contact me. My email address is listed below, and I'd really like to leave you with just one final thought. I've talked to so many students about Drexel and the opportunities that are here for prospective students, and they're always so excited about the number of opportunities. And so I say to you, come join us. Come join us and change the world. Become an innovator, a maker, and a game changer. Because that's what we're doing here at Drexel in biomedical engineering. We're saving lives one device at a time, and we could use your help, so come join us.